Okay, so yeah, let's talk about mirror symmetry today, this application, and you'll see that all the things we have shown you in this week and some of what Pierik showed you will come together. So, I mean, just some general introduction. I mean, when mirror symmetry, of course, arose in physics as a duality of 2A and 2B string theory, and then as a mathematician, you shrug and say, okay, fine. You don't know what to do. But there are mathematical incarnations of this, and that's, I think, what we now understand mathematically is mirror symmetry. So it always has an A side and a B side. The A side is an arbitrary letters for symplectic aspects, and B is for complex geometry. Confusingly, this A doesn't necessarily relate to the A and the B to the B. It depends if you're in the vector multiplet or hypermultiplet side, but that's physics, okay? So anyway, we have two sides, symplectic and complex. And then there's these basic two aspects, enumerative and homological. Enumerative is this very first observation that you can compute the Gromov-Witten invariants on the geometry of one side, so counting curves by doing paired integrals, so integrals of the holomorphic n form over an n cycle and vary the complex structure on a completely different geometry, and that came out of nowhere. So this is what this field started, and then Concevic famously conjectured that the mirror symmetry should also relate the Fukaya categories that had previously defined, suggested by Fukaya. It's an A infinity category. It has a triangulated category associated to it. It should be isomorphic to this, or equivalent to this, to the derived category on the B side. So, of course, this whole field has been kind of plagued by the basic question for which pairs of spaces. And so that's a very basic question. Up to like 10 years ago or so, there was all kind of ad hoc or synthetic constructions. A huge source of examples are complete intersection Calabi-Yaos in toric varieties. So I just came back from a physics conference in Polygon at the beginning of the month, and people are still kind of deep learning how many there really are. Okay, so it's a huge number, okay? There's this Kreuzer-Skarke database, but then you still have to resolve, and that gives different geometries and so on. It's in the, I don't know, 10 to 12 or something. So more than anybody really ever want to care explicitly about. So maybe that was one reason why people never kind of really more deeply, especially physicists, thought about what should be pairs of spaces. But then there are other things, the Berglund-Hübsch construction, which is kind of related to the Bardioev-Borisov, still a kind of toric geometry. And then with Mark Rose, I had a program, still have a program, that started in 2002 maybe, and until 2012 it was basically a synthetic approach and kind of vast generalization even of this kind of Bardioev-Borisov thing that started off with a slightly different, more general kind of discrete data and produce canonically both sides of the mirror. And the story I'm going to tell you now, this kind of intrinsic mirror symmetry story, grew out of this program. So it's my kind of the modern version of that, as you will see. Of course, as a mathematician, the dream result is you would have some A geometry that is not defined by some construction, but by some invariants. Let's say I want a Calabi-Yau. That's maybe just a Calabi-Yau, okay? Or maybe a degeneration of Calabi-Yau. So something that is kind of more natural than just saying, hey, take these equations and do something with them. And it should canonically produce something on the B side, okay? So as algebraic geometers, you would, here's the answer we have. And I hope you agree that this is about as good as we could have ever hoped for as algebraic geometers. So the intrinsic mirrors start with, there are two cases, okay? So the original case is what will appear as variant here, is for proper Calabi-Yau varieties. So complete, maybe smooth varieties with trivial canonical bundle. And then maybe you want some other conditions like B1 equals 0 or so. But, and then there is this other case which, for example, you have a Fano and an anti-canonical divisor. So what we can do is we can take a pair y comma d. Let's take a normal crossings pair. So y would be smooth, d is the normal crossings divisor. Toroidal works as well, okay? So in the log geometry language, anything log smooth over a trivial log point. And then you have a weak log Calabi-Yau condition, which says that, so Calabi-Yau would say you take the log canonical bundle of that. That is ky plus d. And that should be 0. That's an honest Calabi-Yau condition. If you are a birational geometer, you wouldn't necessarily like that because it's essentially the output of the minimal model program, which you would hope to get. And what you typically much more easily write down is something that would fulfill a slightly weaker condition, namely, you get ky plus d is an effective divisor supported on d. So some ai di with ai larger or equal 0. And that works. Yeah, so and obviously the the nicest class would be you take a Fano and an anti-canonical divisor. Okay, normal crossings or toroidal. And then the output of our mirror construction is a family X over a ring that you should think of the complexified Kähler moduli space of this geometry. So this would, in algebraic geometry, you take the cone of effective curve classes, turn it into a ring, complete it, and take the spectrum, okay? And that will be an affine map, and this is actually what you expect in these situations to get. A variant is as follows. You apply that situation to a pair, curly y, curly d, where d contains the central fiber. So then you get a log-smooth morphism from this total space y with the log structure induced by this pair, the divisor, to this curve, and with the log structure given by this distinguished point, the central fiber. So that would apply to the situation where you have a degeneration of Calabi-Yau manifolds, like for the quartics that we saw, right? X product xi plus t times degree of 4 polynomial equals 0. And then t going to 0 is what gives this central fiber the union of 4 copies of P2, as we have seen. And the output would actually be, again, this is still in effect, okay? So I still want k curly y plus curly d to be an effective linear combination of a divisor supported on d. And the output is now a projective family over the same kind of base ring. This curve, yeah, maybe I don't want, this should be an affine curve, okay? We don't get any curve classes that come from sections. Okay, so that can, so this is where the construction works, as you will see. We don't need anything else. You sometimes get results for your mirror that don't look like mirrors at all. And then you have done something wrong. So maybe you have done something, so for example, the dimension of the space you would get, the dimension of the fibers here or the dimension of the fibers of X over this guy has to do with the codimension of the strata of D. So if you want this to have the same dimension as the geometry you start off with, you better have some zero-dimensional strata, okay? So this is some kind of maximal degeneration condition. And indeed, if you look at the kind of Pika-Lefschetz transformation you get in this situation, if you know a little Hodge theory, you can detect this zero-dimensional strata from the Hodge theory. It's called what is called maximally unipotent. And that's a standard assumption you find in early works of mirror symmetry that you need to make the whole story work. So this is a very natural condition, and similarly here. I will show you an example where you see what's happening if D does not fulfill this condition. Okay, so what's the answer? The answer is ridiculously simple. It is so simple that it's embarrassing. It took 40 years to come, or 30 years maybe, to come up with this answer, because it involves an object, a generalization of an object that was that was kind of built mathematically to make sense of mirror symmetry, namely quantum cohomology. Quantum cohomology is this ring built from Gromov-Witten theory. And the only thing that people missed for a long time is you have to make contact to this divisor. So there's a notion of relative quantum cohomology that I'm working on to define in complete generality with Daniel Pomaleano and Mark Gross currently. But we only need the degree 0 part. The degree 0 part of ordinary quantum cohomology, of course, is boring, right? It's just a complex number. There's nothing going on. But once you throw in the divisor, all kinds of interesting things are happening. That's exactly what you need to produce your mirrors. So this thing has a natural ring structure. It's very similar to the ring structure you find in quantum cohomology. And then in the absolute case, you take the spec. Well, it might not be finitely generated algebra, okay? So you need the formal spectrum. It's just a co-limit of rings. But in the relative case, it's an honest proj. And in the final case, it will also be an honest spec. Okay, so that's as good as you can do. And rather than giving you all kind of gory details with how to do this in general, and nobody will understand a thing, I'll just go through one example, okay, and show you with very concrete equations what one can do. Are there questions to this general setup, to the general philosophy, maybe?
So just in the package case, the D that you said it should contain a special fiber.
Yes.
But the plus on the other.
It could contain. So what this actually the example I go through will be the case. So in the honest Calabi-Yau case, you want D to be only the central fiber, but what you can also do is like degenerations of Fano varieties. And then the D would have to be, to fulfill this condition, right? It would still have to have some, contain an anti-canonical divisor on the generic fiber. Okay? Yeah, good.
Is there any heuristic for the Gromov-Witten curves showing up as the
Yes, totally. So in mirror symmetry, you have a mirroring between the complex, so the Kähler moduli and the complex moduli. As a statement like this, it doesn't make sense. The Kähler moduli is something real, complex moduli is complex. So you have to complexify, okay? So you would have, if you have the positive real line or something, or the natural numbers, you would turn it into a C star or C. And this is what's happening here. So if you think about it, if you take the ring and the spectrum, they dualize, right? So if you take the spectrum of the curve classes, that gives a complexified Köhler cone. Yeah? So this is the natural base space you want to see. Of course, you can always base change. I mean, sometimes you want to say, hey, I'm just interested for this one parameter family having to do with one polarization. Then you base change by pairing your curve classes with this Kähler class. Okay. So the input will be a toroidal degeneration of P2 with an elliptic curve, with a cubic, with a smooth cubic. So this is not what people typically do with mirror symmetries. If you ask what is the mirror of P2, people would point to construction done in the early 1990s, Giventhal or Hori-Wafar. So you could look at the mirror, for example, of P2 minus the toric divisor. So that's just a C star squared. So that's a C star squared. And the mirror is also a C star squared. That's kind of boring. But it's, once I add in the divisor D, physicists will tell you that you obtain also a superpotential, what they call a superpotential, which is just a holomorphic function on your geometry. And in this case, that's kind of interesting. The function looks like x plus y plus t over xy, and the t comes from pairing your line class, that's now similar to my answer to Matthias' question, with the Kähler class. Okay, so this is this factor t. That's what you find in the literature. So that would be the mirror of the toric P2. What would we get when we apply intrinsic mirror symmetry to this y comma d? Well, it's very similar. It's compatible with this. You get the degeneration that looks like x, y, z equals t to L. That comes, so x, y, z correspond to the three divisors, actually. So that's a family, a hypersurface in A3 cross A1, the A1 for the parameter. And the T, again, would be a generator of this curve class ring. And it also comes with some W that you see here, that there's a natural function that comes up here, which I didn't write. But you see, if you take T non-zero, you can eliminate one of the variables, and you just get a C star squared. No? So it's the same family. So maybe that's a little boring. Has been done a lot. So more interesting is if we now smooth out this toric boundary and replace it by an elliptic curve. Okay, so that's something classically not known what the mirror maybe is. So what do we get as intrinsic mirror? So oops, that's not so good, because that is one of the cases where we don't have a zero-dimensional stratum, right? So we get actually a one-dimensional mirror rather than a two-dimensional. And well, there are not so many one-dimensional affine rings you can write down, so it's just a polynomial ring in one variable. So that looks totally boring. It is not entirely boring, because the coordinate ring here, our construction comes with a canonical basis of the coordinate ring, and you do get the structure coefficients, and which do have enumerative meaning. So there's a Mark had a student, Yu Wang, and he investigated the enumerative meaning of the structure coefficients in this case. But still, the geometry as the wrong dimension is a little boring, so that's not what I want to discuss. Instead, I want to look at exactly the situation I was mentioning at. I put this in a degeneration. So I take a family with general fiber, a pair P2, comma, and a smooth cubic, and then it degenerates to something that has so that the total space has a zero-dimensional orbit, zero-dimensional stratum. So this is very explicit. So the family I'm writing down looks like this. So you take a degenerating family of what looks like degeneration of cubics, but I do this in a weighted projective space. So I have four variables, x0 to x3. The first three have weight 1. The last one has weight 3. And then the following is a homogeneous degree 3 equation. So x0, x1, x2 minus s will be my parameter, not t. Okay, I reserve t for the mirror side. And then times x3 minus a general degree 3 polynomial in x0, x1, and x2. So what you will see is if s is non-zero, you can eliminate x3, and then you get a nice cubic curve. Okay, so that doesn't look so bad. So you get P2. Sorry, you get P2, and then in there you will also get a cubic curve. So this is this family here. Okay, so this has a projection to the S parameter, and if you look at this total space of this family, that's not smooth. It's also not even toroidal. It has, again, these A1 singularities that come from zeros of this degree 3 polynomial intersected with a double locus of that zero locus. So this looks like this. There's 3 copies of weighted P2s. It's a P2113. And on each intersection, we again have these A1 singularities. We know how to resolve them simply by blowing up in some order. I did in a way that is actually not projective, but let's not worry about it. You can still do it. So that's a scheme that you get. So it has these. So you see here, you get these 3 copies of P1 that are the exceptional curves of this small resolution. So what is my divisor? The divisor is the central fiber. The central fiber has these 3 components, D1, D2, D3. And then I need the thing that is the degeneration of the smooth cubic. So that's a D4. And the D4 is given by x3 equals 0, if I remember correctly. Yeah. So okay. So that is the geometry I start off with. And we will compute that the intrinsic mirror of this looks as follows. Okay, we can actually compute it. So of course, it's an example I chose. So we can compute it. There are various nice things going on that makes it computable. In general, you might just only know that the central fiber, and you know it's a flat deformation of the central fiber, okay? But here we can actually compute it, and you see it has this W that's the same W we had before. It has to do with the superpotential. So it's a non-complete geometry, and W generates the coordinate ring, the ring of, sorry, I shouldn't say coordinate, a ring of functions, of global functions. So this has degree 0, and then you have 4 more variables of degree 1. And there is the equation x by z minus u cubed that we will see as a kind of toric equation. And then something that already reminds you, looks reminiscent of the superpotential if you dehomogenize at u, right? Then at W becomes t times x plus y plus z, little x, little y, little z being capital X over u and so on. Yeah, so this is what this node is. So dehomogenizing at u yields this Hori-Waffer mirror. Okay. Other questions to this geometry, to the geometric setup and the statement of the result? I'm not assuming, I mean, I will go through this and derive how to get this. Okay, so there are a bunch of steps. I think I've subdivided in 4 steps. So the first step is something we know very well already by now, so which is you tropicalize this pair y comma d. So we had this tropicalization of the total space with the log structure having to do with the divisor. So sigma y maps to sigma 1 is r larger equals 0, and we learned there's a map of cone complexes. So it's uniquely given by the fiber over 1. So this is a picture of the fiber over 1. You see this one big cell here that has to do, if I go back, you see there's this one point in the middle. And you should recognize that if I dualize that thing, you become this triangle. That is what you see here. Then there's one direction here that is all the same because it's D4. D4 is reducible when you intersect it with the central fiber, but it's an irreducible divisor on the total space, right? So generic fiber is this elliptic curve. So there's only one ray for that. And that is kind of, yeah, it looks a little funky the way I wrote it. You should really identify all these rays here, yeah? So what you get is a kind of the boundary of a half-infinite prism. You put the triangle on the base and then just go to have these 3 flaps glued together on their sides. The reason I've written it here is that we will see there's also some kind of affine geometry along these edges that flattens them out. Okay, so, and this is the correct affine picture. Yeah, it's a chart, the way, an affine chart is the way I've written it. So this is the intersection with 1. So I've given a bar here to say, to distinguish these intersections with 1. So what sigma 1 means, it's the simplicial cone generated by E1, E2, and E4. Note also that this total space here, the y, is not quite normal crossings over C. It's normal crossings here and here and here, and of course along all these codimension 1 loci. But it's not normal crossings here. You can almost see this. It's not. It doesn't look correct. Yeah. So it's a mild toroidal singularity. Namely for the toric variety with this kind of fan. Yeah, so this is not a standard simplicial cone. It has 1 more integral point in the interior. So yeah, so right. So these, maybe I should have given this. So these are at point 0, -1. That's at point -1, 0, and that's at point 1, 1. So there's 1 more integral point in the middle. Which is 0, 0. In the general case, so this is an honest case where it's kind of log Calabi-Yau, so ky plus d is 0. If you get these some a ideas in here, for some ai larger than 0, you need to further kind of restrict to a subcomplex in here called the Kontsevich-Solomon skeleton in sigma y, okay? But we don't need this here, so if it speaks to somebody, and I know there's at least one person in this room who probably speaks it to, does it speak to, then takes this, otherwise just ignores this remark. Okay, so we know punctured Gromov-Witten invariance, and here's the answer of what the intrinsic mirroring is. So as a module, you take one generator as a module over this ring, okay, over this ring of curved classes. You take one generator for each integral point in this cone complex, in the dual intersection complex of your degeneration you started off with, or your the space you started off with. And that's just it, okay? It's a free module, has to be free. We want a flat deformation, right? So just like this. And the point, of course, is the ring structure. And the ring structure can be very easily written down if you know what punctured Gromov-Witten invariants are. So you have P and Q and R. The integral points of the sigma of y is a set of contact orders. Yeah, you remember we had these contact orders, the things that had to do with the directions of the unbounded legs, the unbounded legs that we had in the tropicalization. So any integral point in this dual intersection complex will be in contact order, positive contact order. So there is a punctured Gromov-Witten invariance with contact orders P, Q, and then not R, but minus R. It has to do with like, okay, you want 2 inputs, 1 output. Might be confusing, but you will see it has to be like this, okay? So you can't write this down with 2010 technology, because at this time, even 2015 technology, because at this time we didn't have punctured Gromov-Witten invariance, but now we do, and that's the answer, okay? So there's a punctured Gromov-Witten invariance, curved class A, so this goes into some power here, T to A, that will go in the coefficient, and then you just write it down, and that's it. Okay, so of course you can always make this definition, and a hard theorem takes a 150 pages paper that was very painful to write, and it would have never been written if it wasn't Mark pushing forward with it all the time. Is that this ring is actually associative? Okay. That's a black box result. You will never have to study this paper, and I'm afraid we spent a lot of time writing it, and now nobody will ever look at it, okay? But anyway, it's true, okay? We did it. So this is it, okay? Yeah, now we can go home, right? So we are done, end of the talk. Well, okay, maybe. But there's more to the story, okay? So first, what does it have to do with our previous mirror construction and all the mirror constructions that were known, like Bacharev-Borisov and these kind of things, and what actually, how do you compute these things? I mean, come on, you cannot compute all this stuff, right? It looks really difficult. Sometimes you can, and in the paper we wrote called Intrinsic Mirror Symmetry, we have a few examples where we actually compute some of these products, okay? But you'll see it's a bit painful, and the control is not always good. So if you want better control, there's an alternative construction with slightly more assumptions that are always true whenever, in all situations, you care about in honest mirror symmetry. That makes this construction works via wall structures, okay? And the wall structures are good because they give you a lot more control and help you in computing things. So I'll show you how this goes. Are there questions to this ring structure here before we go on?
Can I ask you, it's not about the ring structure, but okay, this is some construction, but what makes this the mirror of what you studied? I guess
I'll show you, like the last 2 slides show you why we have schemes of proofs to proving enumerative mirror symmetry and homological mirror symmetry, plus it's compatible with our previous mirror construction, which we know are comparable with Butterworth-Borisov and so on, and mirror symmetry have been proved in great detail for many, many cases over there. Okay, so it fits a philosophy which is, I mean, this may be part of the problem. With hindsight, it's very clear, but it's actually quite a kind of long story why this is the right definition. Okay, it has to do with the Strominger-Zaslow philosophy of mirror symmetry. It has to do with things people have done in symplectic geometry and so on and so on. Okay. Okay. Oh, by the way, this Pirik, in his talk, he had these kind of walls coming in and scattering and so on. This is a kind of particular case of this wall structure, right? So Pirik, in his talk, he had some geometry that was a blown-up toric variety. If you apply the construction here, you see what he was talking about. Okay, so the first step, or step 2, that was step 1, you get this dual intersection complex. Step 2 is we get an affine structure. I mentioned that already on the slide before when I showed you the picture of sigma of y. You get an affine structure on sigma of y away from the codimension 2 skeleton. So obviously in codimension 0 we have these rational polyhedra that has an affine structure, but we have to glue them, we have to know what to do in codimension 1. So how does this work? So the first observation is, I do the normal crossings case, okay? If you're toroidal, you desingularize torically first and it will all work, okay? But I won't tell much on this. So you observe that adjunction tells you that we all learn in elementary school, right, of algebraic geometry, tells you that the intersections of any of these divisors inside the divisor is also log Calabi-Yau. Yeah? So whenever you have this normal crossing situation, there's this inductive structure I mentioned in my very first talk, right? So you have another smooth stratum. In there are the intersections of all the other divisors, which again are normal crossings, and then adjunction tells you that situation is also log Calabi-Yau. So this is good because if you have a zero-dimensional stratum, that's where the assumption comes in here, okay? So before we didn't need that. The ring structure here that just exists. The ring without any further assumptions. But here for this construction we need that. So let's assume we have a zero-dimensional stratum. Then we also have one-dimensional strata. And a one-dimensional log Calabi-Yau has to be, it could be A1 with 1 point, okay? Let's works too, but let's look at the compact case. Then we have P1 with 2 points, okay? That's the only other case. If we have P1 with 2 points, what does this mean? We have, this is a codimension, sorry, so one-dimensional stratum meaning a codimension 1 cone. So codimension 1 cone would be given by E1 to En minus 1. And it separates exactly 2 maximal cells. That's because we have 2 strata. So there's another En and an En prime. And the affine structure is uniquely given by telling, so of course we can use these in a standard basis. And then I have to tell you where you put that. Yeah, so this can be changed by any linear combination of the E1 to En minus 1. And the affine structure would have to tell you where exactly you put it. So we need a formula. And the formula, yeah, so right. This is what this is saying, right? So we have this curve that's given by these codimension 1 simplex. And I have to tell you what En plus En prime are in this affine structure. And here's the formula, okay? So this P1 is this curve class that I can pair with all the other with all these divisors that are in here that intersect that contains a stratum. That gives me a certain number, and I take this linear combination. Looks arbitrary, but this is what you get when you think of toric geometries and think, so you have a one-dimensional stratum in a toric variety and think what the corresponding fan looks like locally. That's exactly what you get. Okay, it's a little exercise in toric geometry. So let's do this in this explicit example. Let's look at the curve D2 intersected D4 in our degeneration. So maybe I should leave back to the picture. So I'm taking D2 intersected D4, okay? So that is this is my stratum. And that is a curve. So this is my first kind of triangle. So semi-infinite here because I put one point at infinity. And I'm wondering where this point goes, okay? So it has to go, it has to have a distance 1 here. So it has to be 2, 1. Well, I intersect with 1, so this is the last coordinate. It's 1 here everywhere. Then this is 0, 1, and 2. And then I put these two on the same x coordinate, and the question is, what's the x coordinate of E1, right? And we will compute -3. So how do we get -3? Let's look at the formula that tells E1 plus E2, these two, are minus D3 times C times E3 minus D4 times C times E4. Yeah, so these are the other rays coming off here. Yeah, so this is the E4 and the E3. So this is the codimension 1 kind of thing here. Yeah, it's that one and that one. So how do we compute it? Minus D3 times C is easy because D1 plus D2 plus D3 is the central fiber. So that has 0 intersection with any curve. Yeah? So minus D3 times C is D1 plus D2 times C. And this is transverse. This gives each one, so we get 2. D4 times C is I think I got the sign wrong here. Is that possible? I'll double check later, but I think it should be D4C. Yes, D4C is right. We get a -3. Okay, so D4 is this elliptic curve. Okay, and C is one component of the elliptic curve. So 3 times C is the elliptic curve itself. So we get the 3 times the whole thing is the self-intersection number of the elliptic curve, which we know is 9. So totally we get 9 over 3 is 3. Okay, so then you plug it in, you get minus 0, 0, 1. That comes from the E2 plus 2 times that, and then minus D4 times that. That's a -3, and you compute the -3 to 1. Okay? So I'm just saying that the intersection numbers of the one-dimensional stratum with all the adjacent divisors tell you some affine structure. And the reason is that you have this inductive log-Calabi-Yau structure that tells you that each one stratum is a P1 with 2 points. That will also be very important later on in the proofs. So one key step in the proof later on that will not be apparent in what I'm saying is that we use Yishan Wu's gluing formula. And if you remember, one good case was when the gluing strata were toric. P1 with 2 points is toric. So we actually happily are in a situation where gluing only happens on maximal strata. I mean, maximal tropical maximal strata. So these are the deepest strata, 0-dimensional points, or next to maximal, which is a one-dimensional, which correspond to the one-dimensional strata. And both of these are toric in these log-Calabi-Yau geometries. Okay. So step 3. What is this wall structure? Again, punctured Gromov-Witten invariants are the star. Okay? So before, wall structures in our program were done by some ad hoc constructions and some algebraic scattering procedures that had to do with it's just algebra with computing commutators in a quantum torus. So you observe that whenever you have a maximal, actually whenever you have any cone, but let's say we take a maximal cone, okay, we're on dimension n, you get a Laurent polynomial ring, right? It's just the ring generated with powers integral tangent vectors. Okay, so each integral tangent vector can be used as an exponent, and when you put it together, you get a Laurent polynomial ring. And a wall would be a real codimension 1 rational polyhedral cone in one of these maximal cones, sigma, and a Laurent polynomial with coefficients in, here I have a p. The p is my ne of y. Change notation somewhere. With coefficients in this curve class ring. So it looks like CP and then a Laurent polynomial We also want, you have this polyhedral cone, a rational polyhedral cone, it has a tangent vector. So or tangent space, I'm writing this as P group, and that takes the integral points. Now you drop dimension by 1, so that gives a Laurent polynomial in one variable less. Okay, so it's isomorphic to this kind of Laurent polynomial ring with coefficients in these curve classes. And the wall structure is simply a union of walls. Okay, so now I'm telling you that with our punctured Gromov-Witten invariants, we can canonically write down a wall structure. And it's very easy to define. So we have these types of punctured curves and some types of punctured curves. So I'm looking at one punctured curves. So there's only one puncture, one kind of point that is kind of has an arrow. Yeah. Like this. Yeah. So it has some bunch of vertices, bunch of edges, and then only one leg that carries the puncture. Okay, that would be our tropical thing. Then you can imagine that there are situations where this endpoint, when you look at the tropical moduli space, varies in an n-1 dimensional family. We call these things wall types. Okay, the type of a punctured tropical curve where this varies in an n-1 dimensional family is a wall type. So for each wall type, you get Gromov-Witten, punctured Gromov-Witten invariants, W and each curve class, right? Over here, you get a punctured Gromov-Witten invariants that we write WTA, like wall type punctured Gromov-Witten invariants. So, and that comes with an outgoing contact order, UT, that I try to draw here. And for some reason, you need to put a minus. So the Z2 minus UT, I'm changing notation again a little bit, is an element of this Laurent polynomial ring here, okay? So obviously, UT is contained in the kind of hyperplane that locally is cut out by the varying endpoints, you know, because it's tangent in there. So, and then there's some lattice index coming up, KT. I didn't write it. It's some lattice index. Forgot to write this. KT, a lattice index. That has to do with the tropical evaluation map. Okay, a tropical evaluation, tropical lattice index. Okay, so this is what your wall function is. And you take all of them, that gives a wall structure. Okay, big deal. Why would you do that? Oh, let me show you one picture what these look like actually in practice. Okay, so here's something that Tim Grefnitz, my student, former student, produced essentially following his thesis project. So there's a Sage code that you can download and play with yourself that computes these kind of wall structures actually from the kind of more algorithmic fashion that we did in our previous work, but we know they agree, and he proved they agree with this kind of canonical wall structure kind of thing. So you see here, these are vertices, and then they sometimes just kind of stuff comes out, but sometimes they come together and then they produce new stuff depending where you go, and it's a huge mess and eventually becomes dense, of course. Yeah. So if you increase the degree, if you bound your degree, it will be finite. If you increase your, because moduli spaces then are compact, but if you let your degree go to infinity, that will be dense. I missed to say this is all genus 0. Whatever I'm talking about today will be genus 0. Okay, so maybe I put this here. Okay, so we have a wall structure. Step 4. When you have a wall structure, you can always construct something, a space in codimension less or equal 1. Okay, simply by gluing together. Actually, that's not quite true. Not whenever you have a wall structure. You need a little bit of consistency. But anyway, so I'll show you what you get. So you can show that the following works. So first, we need to work on a finite approximation. So I don't like dense scattering diagrams. Let's make it finite. That can be done, for example, by working with an Artinian quotient ring. So the P was, again, my notation for the curve classes. And then you take an Artinian quotient, and obviously the ring you're after is the limit of all these rings here, of these Artinian approximations. So then you make the wall structure finite. Okay, so now you have finitely many chambers, kind of, the complements of the walls gives chambers. And for each point, interior point of a chamber, you take a copy of this kind of torus, a thickened torus. So it's a torus over spec Si, over this Artinian ring. Okay, so a little model, very boring. The second local model is a little more interesting, namely when your wall happens to lie in a codimension 1 cell, so in one of these with strata of the polyhedral decomposition, an n-1 cell of your cone complex, then I take this kind of thing. So it looks like a normal crossings degeneration, but twisted with this fp. So the equation is uv is fp times a power of t, and the t power has this, is given by the curve class corresponding to the n-1 dimensional stratum you're talking about. You know, so your wall lives in an n-1 dimensional cone that corresponds to a 1 stratum, isomorphic to a P1, that has a curve class, that's what I put here. And then I get this ring. And then there are gluing maps. So there are first, maybe let's start with the second one because, or maybe we start with the first one. So there are generalization maps from 2 to 1. So if you have something in codimension 1, then of course there's a chamber in codimension 0, in this maximal cell that you can move into. And indeed, you can localize either at U or V. There's some orientation issue here involved, some choices of sites. You see that ring becomes isomorphic to that ring, right? So U and U inverse will be the missing coordinate in the Laurent polynomial. You go from a GM to n-1. That's here, right? That's a GM to n-1 cross spec Si. And then you localize that at U or V, you get the missing GM. So there are these kind of open embeddings of 1 into 2. That's the other way around. What am I doing? So rings the other way, but this 1 and 2 is an open embedding. The more interesting ones are these wall crossing automorphisms that actually look like cluster transformations. Namely, whenever you have 2 of these copies separated by a wall, so something like this. So there's this sigma. Actually, that should be simplicial, right? I'm not writing something simplicial, that's bad. So let's start again. Let's start with sigma, and then you have a wall in here, that's your P. Let's assume it separates a thing. You can go from here to here, okay? And that's what this does. So both these points have a copy of this torus, and they are related by this wall crossing automorphism that depends on this function fp. So it does nothing for monomials that are parallel to the wall. This is what this is saying, okay? And then if you have a primitive vector in this direction, it multiplies it by fp. If the primitive vector goes in the other direction, it multiplies it by fp inverse, okay? So this is an automorphism of these rings that you can use to identify this ring with that one. And you can show that the wall structures that we wrote down are consistent with this. So if there are several ways to compose these things, they all give the same result. So that's something you have to prove. And if you do that, you take the co-limit of all these models here of this category we have defined, this diagram, we get some scheme UI over spec Si that's flat. And we will see later that the complement, sorry, what is this? Yeah, that's the complement of UI. So UI will be an open subset of in Xi, the thing we are after, that has codimension 2. So what we are missing are codimension 2. We have only done something in codimension 0 and codimension 1, not in higher codimensions. The questions on this step? Okay. So then we extend over codimension 2. And the fact is simply, abstractly, you can, in terms of as a matter of definition, you just, let's assume we are affine. Otherwise, I have to do something with sections of line bundles. So let me write this. Maybe where do I write this? So that would be the affine case. So for affine X, you're just interested in the ring of coordinate of global functions, and you remove something of codimension 2, and the whole thing that you will cook up is S2, fulfills Serre's condition S2. So it will be the same to take just the ring of global functions, okay? And that is the ring you want. And then this kind of relative quantum cohomology ring, degree 0, will be the limit of these rings when you take the limit over all these co-Artinian ideals I. Okay, so why does this work? This works because we actually have a basis. Because, well, let's look at our definition, right? So we had this definition before in our abstract definition. We have these theta p's, okay? These now become sections of a line bundle, or in the affine case, just ordinary functions on these ui's. And we can define these functions once we have a Wald structure, and then just look at the ring of functions given by these things, and we see that will define a flat deformation. So the theta p on x0, so we have an x0, if you specialize the construction I've given to I equals the maximal ideal in this complete local ring CP, then you just get a Stanley-Reisner ring, a ring that is naturally associated to a simplicial complex. Slight generalization, because we may not be simplicial if we are not normal crossings. And these kind of canonical elements in this Stanley-Reisner ring can define sections of a line bundle, or rather functions maybe, on this ui's. So let me just give you the formula. Again, we will have punctured Gromov-Witten invariants. So we want to define what theta p is. So p would now be a contact order, okay? So for each contact order, write down our function on ui. So the theta p, I have to give you a function on each of these local models, right? So let me show you what the local model is, what the function is here on these sigma z group. Here's a formula. So now you take a sum over all types of punctured tropical maps, which now has two punctures. One is actually a marked point with contact order p, and the other one is again loose and has some u tau, okay, as before for Wald structures. So this gives you a punctured Gromov-Witten invariant n tau comma a, and you take the sum over these types of punctured tropical curves that we call of broken line type. And it's a similar sum as before, and that defines you an element of this Laurent polynomial ring in each of these charts, and then you prove that this is compatible with a Wald crossing and blah, blah, blah. Okay, so this will give you a ring of functions, and that's why this is successful. Plus, you see, we have this canonical basis of functions that come from with the mirror construction. Okay? Is everybody lost?
I have a question. So, in the proof of associativity, we use this kind of local, let's say, local description of how do you prove the associativity?
So,
use some of these arguments, or it's completely?
Well, right. There are two proofs of associativity, right? So, the proof before uses these kind of, it's similar to Gromov-Witten theory, where you look at four-pointed curves and degenerate in two different ways, okay? You do this logarithmically, and that's a bit headache. Here, these rings, I mean, rings of functions are commutative. So this is implicit. So once you show there are these, we can consistently glue the ui, and we can consistently show that the theta p defined functions or sections of line bundles on ui, there's nothing to prove, right? I'm just building a space, and then we have a homogeneous coordinate ring. Okay. So Okay, so yeah, so how does this is the last slide for the construction, and then I'll say, hopefully I have 2 or 3 minutes to say something on enumerative and homological mirror symmetry. So how do we do this explicitly, right? So this kind of ends the construction here, but how do we do this explicitly? And the explicit construction is via broken lines. If you look at the spine of a punctured tropical map, genus 0 of tropical type T, of type tau here, of these kind of type tau that we had here, okay, with these 2 punctures. So there's one incoming, there was a marked point, and the one outgoing. The whole thing is a tree, so that has a spine. It has some tentacles also, we don't care. The spine is what we call a broken line. A broken line is a piecewise linear path in this fiber over 1, carrying a monomial and bending at most whenever crossing a wall. So you would start with minus p somewhere from infinity. You can parallel transport somewhere, okay? That starts in some cone. And then at some point you hit a wall. You could just go through, okay? Or you bend. What's the rule for bending? Let's do this here. So you can always carry some monomial. So let's assume the monomial inductive. The monomial here would just be z to p, okay? The monomial you start off with is z to p. And then at some point you have a constant, some z to m. You hit a wall p. You apply your theta p, the wall crossing function, to it. You get some expression, some ai z to mi. Pick one of the summands and continue with that one in the direction minus mi. Okay, so you continue with ai z to mi. You in the direction minus mi. That's a certain thing, and then you end somewhere. And what we wrote down here. This sum here turns out to be the sum over broken lines. So you fix a point here, you look at all the broken lines ending up here, and that's the sum I gave you before for the theta function. So what makes it computable in our case? When you stare at this diagram, you will observe there's this big wide region. What this actually is, of course, that's the chart at infinity, right? The one where we did the affine structure computation. But this is what it looks like, right? So this shaded region corresponds to this bounded cell you see here in the middle. There are absolutely no walls there. And all the other walls like point out. Now what's happening if you look at this kind of formula? What's happening if you hit a wall, it will always, well, it could not bend, but if it bends and you have an outgoing wall, it can never continue down. You have only kind of a 0-1 direction to burn. As soon as you bend, you are at least parallel. You will never hit the bounded wall, and you will never go into this bounded chamber. So any of the broken lines that end up in the central chamber are straight. Okay? Not quite true. I mean, they could bend a little bit, but essentially they are all straight. Very close to this one, they are all straight. So what you get, that means you get only a toric relation among all these monomials or sections of a line bundle that corresponds to integral points here in the bounded cell. That gives this first equation that we had, x by z equals u cubed. The second equation, having to do with the superpotential, comes by looking at the theta function that corresponds to this kind of primitive vector. There's an E4 here, okay? Now you look at the bounded things coming in, and what you see is there's one in each direction. So there's one here, there's one here, and there's one here. That gives these 3 terms. You pick up a t power because you have to cross that wall. Okay, that's codimension 1 cell. And that gives this equation. And that's all that there is because we have a flat deformation and we know what the relations are at t equals 0. So this is what this is. When did we start? Did we start late or did we start really on time 11? I didn't check.
We have 1 minute and 30 seconds.
Okay, so maybe I'll go over time 3 minutes. I'll take maybe 5 minutes for 2 slides. So let me just give you an outlook why. I mean, apart that this is compatible with our previous constructions, how do we now think to prove enumerative mirror symmetry and homological mirror symmetry in complete generality and kind of, I think, the way it should be done because it's very transparent. It gives you the reason why things are true. Well, let me first say the following. This mirror construction readily brings in enumerative geometry right from the outset, right? So we construct the mirror from punctured Gromov-Witten invariants. So of course, I mean, it's there's nothing miraculous. That of course that contains some enumerative information about the space you start with. Okay, so I mean, the whole construction already takes out a lot of the miracles of mirror symmetry. But let's try to prove enumerative mirror symmetry in this setup. So we have a Calabi of dimension 3, let's say, okay? Otherwise, it's getting a little iffy to even say what this, how to compute this. And we take for P and we base change to P. Actually, there was I think I missed something for P. I had a base change to P anyway. Maybe P was okay. Anyway, so we base change to N. And then you observe that in the formulas I wrote down, they actually at least work over the rational numbers, and they certainly respect the real locus. So there's a real structure in your mirror, and quite often, in cases we don't fully understand, but it seems to be a key aspect to get good enumerative mirror constructions. So that always holds for toric varieties, for these complete intersections, okay? You have a connected component that is a positive real locus. And if you know a little bit about SYZ mirror symmetry, these positive real loci are sections of the SYZ fibration, okay? So that's what this is, why the real locus is a 2 to n over 1 section of the SYZ fibration, okay? So this is what I wrote here. Then you compute the integral over this positive real locus of the holomorphic end form that comes with the construction. So we also, your wall crossings, they all preserve the holomorphic volume, logarithmic holomorphic volume form d log x1 wedge blah, 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 d log xn. That is this omega t. And you expand, and for general reasons, you see it has a log cube term, a log square term, a log t term, and then some holomorphic term. These coefficients are constants. They're topological. And then you have these two interesting holomorphic functions, and both of them contain the Gromov-Witten potential, okay? So the thing now is, strategy is compute this kind of integral explicitly. Why the wall structure? It sounds a little bit of a daunting task, but we can do it, okay? And we have done it for something like KP2. So the mirror of KP2, I mean mirror of KP2 with Michel van Garel and Helge Roeder. It's an ongoing project. So we have successfully computed the local Gromov-Witten invariants of KP2 by doing this integral explicitly. And at the moment, we are figuring out how this relates to the tropical geometry, and we're pretty close, okay? So it looks like there's a way to compute this, and you get a tropical expression, and they will tell you how to compute closed Gromov-Witten invariants and how it relates to these period integrals. The other one is homological mirror symmetry. That's a lot trickier. I mean, for enumerative mirror symmetry, I'm a bit confident that maybe we can do it even in the intrinsic setup. Let's see how this goes. It's the last slide. So this is with Tim Perutz and Jacob, who is here in the audience. There is so there is something called the Log-Punichen-Salomon-Schwarz morphism that relates this relative quantum cohomology in a Calabi-Yau degeneration situation to something called the symplectic monodromy ring. So if you look at this degeneration y over the curve, you can go around the curve. The whole total space has a Kähler class, and it has a symplectic parallel transport. That gives a symplectomorphism of a general fiber. That would be a Calabi-Yau. And whenever you have a symplectomorphism, there's like late 1980s technology that produces a fixed point Floer homology. And it has so these are these kind of rings, right? Symplectic geometry, not hard. And it has a pair of Pan's product. And the log PSS morphism relates these two. And we are very hopeful to prove that this is an isomorphism without any further assumptions, very generally, okay? So once this is established, everything moves to symplectic geometry because now there's the mirror side is completely out of the picture. Yeah? This is where the mirror side is. This is now, we have to relate this to the Fukaya category. So how does this work? Fortunately, symplectic geometers have done a lot of work in this direction. So there are some technical assumptions that I don't have time to go through. So for example, maybe I mentioned it briefly. So the mirror should be generically smooth. That's not automatic. And then we need a Lagrangian in there that looks like it's a homology sphere and is good Floer theoretically. So if we have a positive real locus in the Y geometry, this would be one of the good cases, okay? And then there's a closed open map that symplectic geometers wrote down from this Floer theoretic ring, the monodromy Floer theory, to the Lagrangian Floer theory generated by the Lagrangian and all its translates, positive translates phi p of L. So whenever it's Lagrangian, you can apply the symplectomorphisms, it kind of produces some kind of Dehn twist, get another Lagrangian. And that is supposed to be an isomorphism. That is also not so hard. And then there is a fantastic theorem by Polishuk that tells you that if you look at these kind of rings, this has essentially unique A-infinity structure. Yeah? So this is this kind of, sorry, is that correct? I should put an X here. Sorry, I'll have to correct this. Anyway, we don't have time. And then, yeah, so why is L and all its translates enough then to produce all the Fukaya category? There's a certain automatic generation criteria or something called core mirror symmetry by Tim and Nick Sheridan that tells you that this is enough. Okay, so the morale is both enumerative mirror symmetry and homological mirror symmetry are kind of within reach in this framework. And intrinsic mirrors give you takes out the kind of miracle out of mirror symmetry. Okay, thanks for your attention. That's it.